We're now going to cover the visitor pattern. In addition to understanding how the visitor pattern works in general, we're also going to discuss how to recognize how this pattern can be applied to enhance the extensibility of expression tree operations. Visitor is one of the most complicated patterns in the Gang of Four book, so we'll try to break it down and look at it from a number of different points of view. The purpose of applying visitor is to perform an extensible set of operations on an expression tree without requiring any changes to the tree itself. Visitor decouples the expression tree structure from the operations performed on it. Let's talk a bit about how this applies in the context of our expression tree processing app. Ideally, we'd like to be able to add new operations to an expression tree without requiring any changes to the structure and the implementation of the tree itself. We'd like to be able to print various values in the tree, evaluate the yield of the nodes in the tree, conduct semantic analysis of the tree, do various kinds of optimization, and so on and so forth. And we don't want to have to keep going back and modifying the way the tree works. Obviously, this is going to be a problem if we try to hard code operations in the expression tree itself or in any of its subclasses of the component node, which will limit extensibility. For example, if you take a look at this diagram, we'd like to try to avoid hard coding print and evaluate and optimize methods directly into the expression tree because it's going to be difficult to make changes to that without breaking the open-closed principle. We'd like to try to keep things as closed for updates as possible and be able to make changes without modifying what we've already got. We'd also like to be able to find a way to work around one of the problems we saw when we discussed the iterator pattern implementation earlier. In the example I showed there, we were able to go through every node in the tree and do something with it, but it required the use of explicit downcasts to access the expression tree nodes, which is also something that's likely to cause problems over time. It'll limit extensibility because invariably if you make changes that modify the way in which the tree is structured and your code relies on downcasting, it's going to cause trouble at some point because you're going to end up with a case you didn't expect. A downcast is really not that much different from an if-else statement or a switch statement, and it tends to bind you very tightly to a particular structure and a particular representation. So what can we do to avoid these problems? Well, what we're going to do is we're going to decouple the operations on an expression tree from its API and its structure. Let's talk about how we're going to do this. This is somewhat complicated, so we're going to break it down into a series of steps. The first thing we're going to do is we're going to create a hierarchy of so-called visitors that will define visit operations that know how to perform certain operations, certain processing on each type of expression tree node. So as you can see here, we have a visitor base class, and it'll have a number of overloaded visit methods, one for every different kind of subclass in the expression tree hierarchy. And then we'll go ahead later and we'll make different kinds of subclasses of visitor: print visitor, evaluation visitor, semantic analysis visitor, optimization visitor, and so on. The next thing we do is we define an accept method in the expression tree class API that will be passed an instance of a visitor subclass. Now, if you think back to what we talked about earlier when we were describing composite pattern and the bridge pattern, we already foreshadowed the use of this accept method. Every node in the composite implementation hierarchy, the component node implementer hierarchy, had an accept method that took a visitor. Likewise, the expression tree abstraction has an accept method that takes a visitor as well, and it simply forwards it to the appropriate implementer in the implementation hierarchy. Now, during the iteration over the expression tree, as we're using the iterator pattern, we're going to call accept on each tree node and pass in the desired visitor instance. So as you can see here, we're going to make ourselves a visitor for printing, and for every element that's in the tree, we're going to go ahead and call the accept method passing in the print visitor. That accept method, of course, will forward to the appropriate component node subclass. And finally, and here's how it all comes together, the accept method that's implemented in the component node hierarchy will call back to the visitor's visit method, passing in the corresponding node in the expression tree to perform the operation, passing itself in fact, to perform the operation. So just to take a simple example, here's the leaf node class that extends component node. And we're looking at a snippet of its accept method where it's passed in a visitor as a base class, and it turns around and it says, visitor, please visit me. And by doing this, this indirection avoids hard coding the operations into the expression tree nodes themselves. Notice how the actual visit method that's dispatched is going to depend on the concrete type of component node. In this case, it's a leaf node. And this ability to select the appropriate visit method via method overloading is called static polymorphism. And we'll come back and talk about this when we get a little further into the pattern. I just wanted to note it at this point. So here's what the visitor interface might look like. We can specify an extensible set of operations that can be performed on each subclass of component node in an expression tree. And the interface essentially contains a visit method that takes as a parameter each of the different kinds of subclasses in the component node hierarchy. So we have a leaf node version of visit, composite negate node version of visit, composite add node version of visit, and so on and so forth for all the various nodes in that composite hierarchy that actually do something interesting. From a commonality and variability point of view, we have a common set of visit methods, one for each implementation of component node. From a variability point of view, we can subclass this interface or implement this interface in order to define different behaviors for these different types of visitors. Here's an example of how the visitor implementation hierarchy might look. This class hierarchy implements operations that are performed on subclasses of a component node in an expression tree. So as you can see here, we have the visitor interface we just looked at, and then we can subclass this to provide different behaviors for printing, different behaviors for evaluation, and so on and so forth. What makes this so powerful is that the visitor implementations actually define the operations that affect the tree. These operations are not defined in the expression tree API. They're defined by the visitor subclasses. And that way, the expression tree API can remain fixed and stable, and then we can vary the processing that takes place on an expression tree by creating new implementations of visitor. The way in which all these different pieces fit together is actually described as a pattern in the Gang of Four book called the visitor pattern. The intent of this pattern is to centralize operations on an object structure so that the operations can vary independently, but the whole system still behaves in a polymorphic way. The basic idea here is you want to be able to add new capability without affecting the underlying composite structure. You should consider to apply this pattern when certain things happen. When classes define many different unrelated operations, when the class relationships and their structure change rarely, but the operations on the structure do change, and also when algorithms want to keep state that's updated during traversal, and you don't want to store that state in the actual underlying composite structure that's being accessed by the various algorithms. As I mentioned before, this is a complicated pattern, so let's take a look at the structure. That'll start to help explain things a little bit. What makes this so hard, by the way, is the fact that we've got two parallel inheritance hierarchies, as well as the use of dynamic binding, as well as static polymorphism through the use of overloaded methods. Let's take this and break it down one element at a time. First thing we'll talk about is the visitor hierarchy. So we have a visitor hierarchy that has a method for every different subclass in a composite or element hierarchy. In our case, we have a visitor base class, or interface actually, that defines the methods that appear in the composite. We then go ahead and subclass or implement that visitor interface in order to define various concrete visitors, things like evaluation visitor, print visitor, and so on and so forth. That's one hierarchy. That's the operation hierarchy or the visitor hierarchy. There's a parallel hierarchy that's rooted in element, and every element in this composite structure is going to have an accept method. So in our case, the root, which corresponds to element, would be the component node. And then we'll have a number of different subclasses of component node or element, which actually fill in what happens with the actual accept method implementation. So we have a composite add node, a composite binary node, a composite unary node, and so on. And these all inherit from component node, and they fill in an accept method that knows how to visit the appropriate node based on their actual type, using the visitor that's passed in as a parameter, the call to accept. We'll talk about this a bit later. This little dance between these different elements is called double dispatch. We'll talk about that in a second. Here's a diagram from the Gang of Four book that attempts to show the dynamic interactions or collaborations between the various roles in the visitor pattern. So as you can see here, you have some kind of application that calls an accept method on the nodes or the elements in a composite, passing in the visitor, and interactions take place, and so on and so forth. While this is from the Gang of Four book, I personally find it to be a little bit less than enlightening because it doesn't really give you enough detail to make sense out of the interactions between the various parts. So we're going to look at a more concrete example of how to apply this pattern in the context of our expression tree processing app and Java to make it more clear. So let's talk about how we could actually implement this in Java, and we'll do it a couple different times. We'll first talk about how we could do this for print visitor, and then we'll talk about how we could do it for evaluation visitor, because they're similar in some ways, but they're also different in others. The print visitor class prints out the character code or value for each node in the tree without requiring the use of any downcasting. Here's how it works. We define a print visitor class. It implements the visitor interface and defines implementations of various methods. For every relevant component node subclass, there'll be a corresponding visit method that takes that node as a parameter. We can then use a print visitor instance with any traversal algorithm. So we go ahead and use a factory to make ourselves a print visitor, and then we're going to go ahead and create an iterator with whatever order we happen to want, in order, post order, pre-order, level order, and whatnot. And we iterate through the particular order using the strategy pattern we talked about before. And at every step along the way, for each node in that traversal, we're going to have it accept the print visitor. The accept method, of course, will forward to the implementer's accept, which itself then turns around and calls visit this. So let's take a look and see how this might work as an interaction diagram. Iterator controls the order in which accept is called on each node in the tree. And that's because it's using the strategy pattern to figure out the traversal order. So you can see how we're going to start out by having the iterator say accept on one of the nodes in the tree. Let's say, for sake of argument, that that is a leaf node. So the leaf node then turns around and it says, visitor, please visit me. And because it's a leaf node, because it's got the type leaf node, when this happens, the leaf node implementation of this thing will then turn around and get out the value and print the value. Next thing comes along. Now we're going to go ahead and call accept again on, this time let's say it's a composite negate node. So it's not a number, it's a minus sign. When this happens, it'll call the accept method passing in the print visitor. That will turn around and say, please visit me. And the visitor will say, aha, you happen to be a composite negate node, so I know how to visit you. And what he'll do is he'll turn around and call something that will print out the minus sign. And that will then print that result out. So that's one example of how to use the visitor pattern. Here's another example. This time we're going to use the evaluation visitor. Once again, we have an implementation of the visitor interface, except this time, rather than simply do something real easy, like printing each element, we're going to evaluate the nodes in the expression tree in order to figure out what the yield of the tree is. And to make this easy, we're going to assume we're traversing the tree in post order. If you traverse an expression tree in post order, then you'll end up with a traversal that looks like what we show on the screen, where it's 5 minus 3, 4 plus times. And if you do this, if you use a post order traversal, you can use a stack. In our case, we're going to use a Java stack to keep track of the values that are being computed during this traversal. And so what'll happen is we go through, whenever we see a number, we're going to push the number onto the stack. Whenever we see an operator, be it binary or unary, we're going to pop the appropriate number of operands off the stack, apply them to the operator, and push the result back onto the stack. So the example here on the slide illustrates how we're starting out with the number 5. We pop that off the stack and negate it, getting a minus 5 on the stack. We see the number 3, we push that onto the stack. We see the number 4, we push that onto the stack. Then we see the plus sign. We go ahead and pop off the 3 and the 4, add them together, push them back on the stack, and then finally we have minus 5 and 7 on the stack, and when the multiply operation is seen, it pops both those numbers, multiplies them together, and then pushes the result, the yield, minus 35, back onto the stack. Here's what this looks like if you were to take a look at it from an interaction diagram point of view. Once again, the iterator is controlling the order in which accept is called on each node in the tree, using, in this case, the post-order traversal strategy. So as we're traversing through the tree, we're going to go ahead and accept the eval visitor, and then that will go ahead and visit each node. In this case, it's a leaf node, so it says, visitor, please come and visit me. And what the visitor says is, aha, you are a leaf node, and therefore I'm going to take your value and push you onto the stack. Later on, when we come a bit further, we're going to have, in this case, the composite negate node, and that will say, visitor, please come and visit me. And the visitor says, aha, you happen to be a composite negate node, and so for you, I'm going to pop the current item on the stack and then push the negation of that value back onto the stack. And the nice thing about this is there's no downcasting in the implementation. We're now going to talk about how to implement the visitor pattern in our expression tree processing app. This pattern has a number of different parts, and so let's start by looking at the core piece related to the visitor interface itself. Here's the visitor interface. As you can see, it's just a good old Java interface, and it defines visit methods for each of the interesting nodes that are subclasses of component node in our composite pattern implementation. We have a method that knows how to visit a leaf node, a method that knows how to visit a composite negate node, composite add node, composite subtract node, and so on and so forth. So that's the basic visitor portion. Let's now take a quick look at a couple of different implementations of visitor. First, we're going to take a look at the simplest one. This is print visitor. As you can see, print visitor implements visitor, and each of its visit methods print out the corresponding value for that particular type of subclass of component node. For example, when we visit a leaf node, when we're printing it, we print out the value of the node itself. When we print out any of the other kinds of nodes, when we're in print visitor operation mode, we're going to simply print out the value of the operation, be it a unary negation, a binary plus, a binary subtraction symbol, and so on and so forth. So as you can see here, printing is very straightforward. We're just printing out the right value. A more interesting example of this is something we'll see in our evaluation visitor. Once again, evaluation visitor is a visitor. It implements the visitor interface, except it's done in a more sophisticated way. It allocates a stack of integers, and then each of the visit methods, when they're called, does something on that stack. By the way, evaluation visitor's implementation assumes we're doing a post-order traversal of the tree. Otherwise, it wouldn't work properly. You could implement other types of evaluation visitors for different orders if you'd like. So if we visit a leaf node, we simply push the node item onto the stack. If we visit a composite negate node, if the stack has something in it, we pop the top item of the stack off, we negate the value, and we push it back on the stack. And similar things are done to visit with composite add nodes, composite subtract nodes, composite divide nodes, and so on. The main difference being that we end up popping two elements off and then apply the operation and push it back on the stack. So when we're finally all done traversing a correctly formatted input expression that corresponds to a correctly created expression tree, there should end up being one item on the top of the stack, and that will be the actual value that corresponded to the yield of the expression. So here's the total method. As you can see, this checks to see if the stack is empty, and if it's not empty, it returns the top element of the stack, which would be the value that was computed for the expression tree. So that's essentially the evaluation visitor and print visitor subclasses that implement the interface of visitor. There's some other pieces that you also need to be aware of to make sense of this. We've talked about some of this stuff before, so I won't go through this in detail, but just take a quick look at component node. So if you take a quick look at component node, you'll see how it defined an accept method that took a visitor. And this is just a placeholder. It doesn't do anything. More interesting things start to happen when we take a look at subclasses of component node. For example, here's leaf node, which is a component node. If you take a look at its accept method, and this, by the way, is true for every single one of the other subclasses of component node, they all have accept methods that look exactly the same. They take the visitor argument that was passed to them, and they say, visitor, please come visit me. And of course, the me in this case will correspond to the concrete type of the subclass. So when it visits the leaf node, the visit method on visitor will be called that corresponds to leaf node. So if we go back over to visitor, you'll see that it has a visit method that knows how to visit a leaf node. And all these methods are all defined in exactly the same way because they're all relying on double dispatch and the visitor pattern in order to be able to do the so-called static polymorphism that we talked about in the videos. Just one more piece of the puzzle here to kind of pull it all together. We'll come back again and talk about this later. This is part of the state pattern implementation. When we want to print a tree or we want to evaluate a tree, and you'll see how this gets done later, here's what happens. The print tree method gets called. It passes in the expression tree to print. It passes in the traversal order request, does a few funky things to keep track of whether we have told it explicitly to do in order or not, kind of make life easier for the end user. And then depending on what we've got, we use our visitor factory, which we'll talk about when we talk about factory method pattern, to make ourselves the print visitor, and then we're going to iterate in whatever traversal order was passed in by calling the make iterator factory method, which returns the appropriate iterator strategy. And for every element that we are iterating over in the expression tree, we're going to tell this thing to please accept the print visitor and to be able to print out the value of that node. Now, what's interesting about this is just the high pattern density of the solution. We've got the use of factory method here. We've got the use of iterator. We've got use of strategy. We've got use of visitor. We've actually got use of the bridge pattern because what's actually returned by the next operation here is an expression tree, which has an accept method, which then forwards to the appropriate method on the component node hierarchy. So this is what it looks like when it's all said and done. Very concise, very clean. Notice that there's no need for downcasting here. All of the downcasting is handled implicitly by the use of static polymorphism in order to be able to resolve the actual type of the subclass element of component node that's being dispatched by the accept method. So it's a very clean solution, and we'll come back and talk about these other patterns a little bit later, but I wanted you to see how it all fits together, how the various patterns relate to each other. Now that we're done looking at the expression tree application's use of the visitor pattern, let's talk about some of the consequences of applying this pattern. One of the good things is flexibility. The algorithms that are embodied by the visitor subclasses and the structure of the object, in our case the expression tree, are relatively independent. For example, if we want to add new visitor subclasses, we want to come up with new ways to visit the tree, above and beyond printing and evaluation, that won't have any impact whatsoever on the expression tree composite structure or any given realization of an expression tree. Those things are left separate. Likewise, we have nice separation of concerns. The functionality for the operations is embodied in the visitor subclass instances. That's where that information resides. They can store state. They can do various kinds of processing. Once again, we don't make any impact on how the tree is implemented, how it's structured, and so on. Things are localized in a very clean way. There are some downsides, however. One of the problems is the circular dependency between visitor and element interfaces. So, for example, if we come along and we add new subclasses to component node, that will affect the visitor API. So in other words, if we were to come along and add some kind of new node, like we added something like a posit mod node for the modulus operator, we would have to go through all of our visitor methods and add visit composite mod node, and that might be a pretty extensive set of changes. So this pattern, as you can tell, works most effectively if the structure doesn't change very much, but the operations change. From an implementation point of view, one of the keys to understanding this pattern is to make sense of something called double dispatch. Double dispatch is a mechanism that dispatches a function call or a method call to different concrete functions or methods depending on the runtime types of two objects involved in the call. Some programming languages support this natively. In fact, some programming languages support multi-dispatch, where you can actually call a method based on the types of more than two objects. For our use in languages like Java and C++ that do not provide multi-dispatch or double dispatch support natively in the language, we have to implement it using a pattern. And so as you can see here on the slide, it illustrates how the double dispatching works. When you have the accept method called on one of the element subclasses with a visitor, it says, hey, visitor, please come and visit me. And when it says visit me, the visitor then knows what the actual type is, because it's a subclass of the base class. It's composite add node of component node. And the evaluation visitor or the print visitor or whatnot knows how to handle the appropriate subclass. It's baked in to the visit method that's defined on that class. And so those two things put together are what's used to determine which method or methods get called. There's also some interesting trade-offs related to interfacing to elements of the object structure. We've been showing an example that's pretty much the canonical example out of the Gang of Four book, where you have different visit methods for every type in the element object structure. It's also possible to generalize that a bit to have a much smaller number of methods. You could have a visit method that takes one type, say the base type or the super type, say component node, and that will make your interface much, much narrower in terms of the number of methods involved. The problem with that, of course, is now you have to start using type-safe downcasting internal to the visit method to figure out what you've actually got. So you're kind of trading off verbosity for type safety and so on. Interesting known uses of the visitor pattern. One of the ones that we've used in my own experience for many years has been in compiler backends that we've written for some of the middleware that we've developed. We ended up using the visitor pattern to make it possible to have different ways of taking the internal data structure, something like the parse tree that we talked about in the context of the interpreter pattern and builder pattern, and then define different visitors that will go and visit that parse tree and then generate different kinds of output, generate Java output, generate C++ output, generate different mappings to different versions of middleware and so on and so forth. So there's a paper you might want to take a look at to learn more about how this works. All the source code, of course, is available too that may be useful as well. So to summarize the visitor pattern, visitor works together with some other patterns, most notably iterator with a little help from strategy and bridge and factory method as well, to traverse the composite-based expression tree in a flexible manner and perform designated operations in an extensible way. And this grouping of patterns helps to simplify adding new operations without affecting the structure of the tree or the instances of the tree that we've created.